Welcome to this movie on statistical mechanics. I'm Jos Thijssen and I've made this movie for my students of the course Advanced Statistical Mechanics that I teach at the Technical University of Delft. So this movie will be on the canonical ensemble, which is a very important ensemble in statistical mechanics. It describes systems that are kept at a constant temperature, constant volume, a constant number of particles. So I will first derive the probability distribution of the canonical ensemble, and then I will look at various aspects of the ensemble, such as the energy fluctuations, and finally I will consider the partition function of an ideal gas and the harmonic oscillator. I hope it will be a useful movie. I will start with a rather straightforward derivation, a standard derivation of the probability distribution of configurations in the canonical ensemble. So we look at a system that is kept at a constant temperature. And the first question is, of course, how can we do that? And that we do that typically by embedding the system into an environment which is at a certain temperature. For example, if I have a coffee cup and I put it in a room which is kept at 20 degrees Celsius, then after some time the coffee cup, even if it was initially, say, 60 degrees Celsius, it will go to 20 degrees in the end, because the room and perhaps the adjacent room with which it is in contact, they are altogether much larger than the cup itself. So we look at a small system, that's your coffee cup, inside the environment, which is the building you are, and we can consider the building so big that it doesn't matter whether it's in contact with another system or whether it's isolated. So the total system, we consider that to be isolated, because then we can apply the microcanonical ensemble. So we have the environment, and that's E. We have the system S, and we know that the energy of the system and the environment together are equal to the total energy, and we consider the entire system as isolated from the environment, so that total energy is fixed. Now we know that for a system at fixed energy, any state inside that system has the same probability to occur. So if the state of the system is xs and the state of the environment is xe, then the state of the environment plus the system can be written as xs, xe, and that is the state of the system as a whole, and all these systems have the same probability of occurrence, and that means that a probability P to have a configuration xs, xe, so that should be just independent of xs, xe, because it's constant, it's independent of the state we are looking at, and all the states of system plus environment can be written as xs, xe. Now what do we then get for the probability to find the system in a state x small s? Well, we know the probability for the environment plus the system, so we just sum over all the states of the environment, because we are not interested in those, and then we have the conditional probability that the system, the small system, is in a state xs. We know that this p here is a constant, and so if we sum over all the xe's, we have that constant times the number of states accessible to the environment. And the number of states accessible to the environment is denoted by omega, and that is a symbol that we have met before, because the omega is related to the entropy. We know that S is K times ln omega, and if I invert that relation, I can relate omega to, I can write omega as E to the power S of the environment, E of the environment divided by KB. So the probability of a particular state of the system plus environment is independent of that state. The probability for a state of the small system is of course not independent of what happens in the small system, and we have just calculated it to be proportional to E in the power entropy of the environment at energy of the environment divided by KB. Now we have this rule here that this condition that EE plus ES is the total E, and that's fixed. And so what we do is we write the energy of the environment as the total energy minus the energy of the system. And then, because this system is a lot smaller, the typical energy in the system is a lot smaller than the total energy, we can Taylor expand this. And so the first term is as E evaluated at the total energy. So that would be if all the energy was in the environment and no energy in the system. And then we have a first order Taylor term, and I've split here the exponents. So the first order Taylor term gives me minus ES of XS times the derivative of S with respect to E. But we know exactly what this derivative of S with respect to E is, because we know from thermodynamics that it is 1 over T. And so we can write then the first term here as a constant, and the remainder is minus the energy of the system when we have the system in a state XS, and we divide that by kBt. And so this is the probability for a particular state XS of the system which is in contact with a large environment, a much larger environment, and this probability distribution is well known. It's the Boltzmann factor. Now the constant that occurs in front of this exponent, that's 1 over z, and we need to adjust 1 over z in order to normalize this probability distribution. So if we ask what the constant is, we just add all the p's of all the states of the system. So we sum over all the states of the system, and then we calculate these p's, and that should give me the expectation value of 1, which is simply 1. And so if I put that in, I immediately find that the z is a sum over the states of the system, E in the power minus ES XS over kBt. So it's a sum over all the exponentials. And this is called, this z is called the partition function. Now on a side note, I have only mentioned so far, I've used a symbolic notation where the sum over the states accessible to the system is denoted as a sum over some x. And you should always realize that this is can be a much more complicated thing. So it can be proportional to d3 and p, d3 and q, and we have seen that if you want to make this perfect, you should put an n factorial and an h in the power 3n in the denominator for proper normalization, or we should take a trace over a quantum mechanical trace over the operator, and so this is just a kind of symbolic notation. Now, whatever the states of the system are, I could always do the following. Suppose I take all the states of the system and I calculate, and all these states, they have a certain energy. So in quantum mechanics I need the eigenfunctions of the Hamiltonian as states, and in classical mechanics, once I know the p's and I know the q's, I know the energy. So for each state I can calculate the energy of that state. And now I look at all the states that occur in a small interval dE. So we have seen that that is the number of states accessible to the system, so that's omega e. And so what you should have in mind, the picture here, is that if I have a sum over x, I have a sum over, for example, some discrete energies, and there may be many energies here, and there may be much fewer energies over there. And so, if I sum over all the states, I could equally well integrate over E, provided that I multiply by the number of states that I can find in each interval dE. Now that number of states can be written as e to the power s over kb, as we have seen before. And so if I want to calculate a partition function, which is the sum over all states of e to the power minus e over kbt, I can replace that sum by the integral if I include here this omega of e, which is called the DOS, the density of states. Now, in order to make progress, we need to go through a little bit of math. And what I want to do is I want to find a formula for evaluating this integral, which is the integral of n times a function of x, fx, integrated over the x, and I have sketched f here, which is a function with a single maximum at x star. And n is a large number. Now we expect the integral to be dominated by the maximum, so we expand f in a Taylor expansion around x star. So we first get the value of f at x star. We would get normally a first order Taylor expansion, but that expansion term, but that vanishes because the derivative of f vanishes at the maximum. And so the first non-zero term is then a second order term. It's a half times delta x squared times the second derivative of f at a point x star. So we write x as x star plus a deviation delta x, and then this is the second order Taylor expansion. Now the n if fx star, because x star is a fixed point, that's a constant, we can pull that in front of the integral. And furthermore, because the f has a maximum, its second derivative is smaller than 0. And so we write that as minus a, where a is positive. And then we see that we have a Gaussian integral over dx. And it doesn't matter because the integral runs from minus infinity to plus infinity. It doesn't matter whether we integrate over x or whether we integrate over delta x. And so this Gaussian integral can be evaluated straightforwardly. This is the result. And then I can write that result also as a contribution in the exponent. And I get then a logarithm of 2 pi over na. 2 pi over a is then a constant. And the n occurs with a logarithm. And the logarithm of n is much smaller, much smaller than n itself if f gets big. So we can approximate this by e to the power n fx star, and this is the most primitive form of the saddle point approximation, which aims at calculating integrals over functions occurring in an exponent with a big prefactor. Now what does this have to do with my partition function? Well, both the e and the s, they are large because we are looking at thermodynamic systems, and e and s are extensive variables, so they scale with the system size. So it makes sense to approximate this integral using this saddle point approximation, and that means that we have to evaluate this integral at the maximum of the exponent. And the exponent is minus e over kbt plus s over kb. So there it is, minus e over kbt plus s over kb. That's my function f, which I have to evaluate. And so if I take the f dE is 0, then I get, first of all, when I take the derivative of e here, minus 1 over kbt. And then if fs would be an equilibrium state, then the SDE is 1 over t, and we see that that is indeed 0. So apparently the maximum of the exponent corresponds to the equilibrium value for the energy. And this affects the equilibrium state of the system. And so if we calculate that z for that particular state, so E star is the equilibrium energy that we have in the system, we get e to the power minus e star over kbt plus s e star over kb, and we can write that as e to the power minus e star minus ds over kt, and that is e in the power minus f over kbt, where f is the free energy. And so we conclude from this that F is minus kBt times log z. And so that means that we can now always, in principle, calculate the free energy of a system. So F is the Helmholtz free energy. And the recipe for calculating F is now sum over all the states of the system. And what do you need to sum? You need to sum, I will call it here. You need to sum over all the states of the system, and then e to the power minus beta er. And if I've done that, I know z, and then I know f. Nevertheless, for non-interacting systems, this is a very difficult task, and it has been carried out analytically only for a handful of models. And for non-interacting systems, usually you can make progress quite easily. And so that's what we shall see at the end of this movie. Okay, so let's summarize what we have so far. We know that in the canonical ensemble, where we keep the energy of the temperature of the system constant, we have PR is e to the power minus beta er, and beta is written as 1 over kBt. And we need to normalize it by dividing over the sum of all the states. So this is r primed, e to the power minus beta er primed. And this denominator, which is in fact a normalization factor for the PR, that is the partition function. It's just a sum of all the states the system can be in, e to the power minus beta er. Beta is 1 over kt. And once we have calculated this object, the partition function, we know the Helmholtz free energy. F is minus kt ln z. And so let us look at the specific heat for such a system, and it turns out that the specific heat is related to the fluctuations in the energy. And to see this, we first give the general rule for calculating an expectation value of some quantity A. We take A in the state R and we multiply that by the probability to be in state R, and we sum over all the states. So it's the standard way of calculating expectation values. And now we apply that to the energy. So the energy is the average value of ER, and so this is the expression for the energy. And now let's calculate something weird, the derivative of the logarithm of z with respect to beta. And let me put here again that z is the sum over r of e to the power minus beta er. So using the chain rule, I get 1 over z is 1 over z dz d beta, and dz d beta, so here is the 1 over z, dz d beta gives me a minus er here, and so I get minus 1 over z, and then the sum over er, e to the power minus beta er. And this is precisely minus the expectation value of er, therefore it's minus the average energy. And so we see that we have a simple formula for the energy. It's just minus d ln z dB. Okay, then we go one step further and look at the specific heat, which is defined as the SDT at constant particle number and volume. And we have seen that that can be also be written as dE dt, and because beta is just 1 over kt, we can write this as dE d beta times d beta dt, and d beta dt, beta is 1 over kt, we get minus 1 over kt squared times dE d beta, and here I will again specify that we keep particle number and volume constant. Now let us consider this term, we know that the energy is given as 1 over z ER minus beta ER. And we need to take the derivative of this with respect to beta. So one derivative comes from this z, and the other derivative comes from this beta here. So let's first take the derivative coming from this one. So if we take the derivative of 1 over z, we get minus 1 over z squared, but we had already a minus sign. And then we need to multiply by dz d beta. Now this term here is already dz d beta. We get a second dz d beta, and so we have a dz d beta squared here. So that's the beta derivative coming from this z. There is a second beta derivative from the exponent here, and if we take that derivative, I get a second r inside the sum. So this is the second term. Now we know that the energy is 1 over z dz d beta, and here I see the square of that expression. So this is just the average value of the energy squared. Okay, so this is the average value of the energy. I don't always put the brackets there. But if I would restore the brackets, then we see that here I have the expectation value of the energy with a squared. And this, by definition, is the expectation value of the energy squared. So here the energy squared is inside the brackets. And it's well known that this gives you an expression for the fluctuation in the energy, dE squared, and we have still this factor 1 over kBt squared in front. And so we see that this was the specific heat, therefore the fluctuation in the energy itself scales with the square root of CV. And remember that, recall that CV is an extensive variable, so it scales with the system size. So the fluctuations in the energy, they scale with the square root of the system size. And if I take now as a parameter the number of particles, then we see that dE scales with the square root of n, E scales with n, and so the relative fluctuations, they scale like 1 over n, a square root of n. And so if n is a macroscopic number, it's typically 10 to the 24th, then this could be 1 over 10 to the 12th, for example. And so it shows that although we relax the energy in the canonical ensemble, it can take on any value. If we calculate the fluctuation, so the width of the distribution that we would see in energy values, it's extremely, extremely narrow. So it's almost as if the energy is completely fixed, because the fluctuations in the energy that we will measure in a macroscopic system are extremely small. And so this relation that we have just seen, it's the simplest form of a static fluctuation dissipation theorem. Now we move on to study the entropy in the canonical ensemble. The entropy can be calculated from the free energy, which is minus kT ln z. And we know that the F, it's the Helmholtz free energy, is defined as E minus ds. So we can calculate S as E minus F over T. And using this expression for F, we can also rewrite this as the expectation value of ER, which is the energy in state R, plus KT times ln z. And now, just as a reminder, we have that the probability for state R to occur is e to the power minus beta ER divided by z, the partition function. And if I invert that relation, I can write ER as minus kBt times ln the product of z and PR. And so that's what we are going to put in this expectation value. It's not something which is really obvious to do, but it turns out that it gives us a very nice result, a very nice expression for the entropy. So if we put it in the entropy, here we have the minus kt times the expectation value of ln(z) times PR. So we first get an ln(z), and that cancels against the ln(z) that was already there. And so we are left with minus kt times the expectation value of ln PR. Well, how do we calculate the expectation value of ln PR? We just sum over all the states, probability for the system to be in that state times the ln PR, of which we want to find the expectation value. The t's cancel, and so this is what I'm left with. And in information theory, that's known as the Shannon entropy. In statistical mechanics, is known as the Gibbs expression for the entropy. And so it's different from the entropy expression that we have seen so far, which was that the entropy is just k ln omega. It's k times the log of the number of states. But that was calculated for the microcanonical ensemble, and the microcanonical ensemble was the ensemble in which we fixed the energy. In the canonical ensemble, we really relaxed the energy. And so if this expression for the entropy is correct, the first thing we should do is check whether it gives us the same result as we already know to be correct for the microcanonical ensemble. Now, in equilibrium, the S always goes towards its maximum. So what we need to do is to maximize S with respect to all these probabilities. And so then we should find, so the aim is to find those probabilities which maximize this function S. And if we fix the energy, then we allow only states R at a fixed energy to participate in this sum over the number of states. But there is a catch here. We cannot just calculate the derivative of S, because there is a constraint which is to be imposed on these PRs. And that constraint is that they should give us a normalized probability distribution. So if we take the PRs and we sum over them, they should add up to 1. That's the normalization condition. And so the method that we use to maximize S under a constraint is the method of Lagrange multipliers. And it works as follows. We do not maximize S, but rather we maximize the function f, which is S minus lambda times the constraint. And lambda is called a Lagrange parameter. Or a Lagrange multiplier. So for each constraint that we impose on the system, we have a Lagrange multiplier, and some people would like to add also here the plus lambda, because there is a 1 on the right hand side, and usually constraints are formulated as something is 0. So for example, the sum of a PR minus 1 is 0, but it turns out that that is irrelevant. So this is the correct, this can be used to maximize f. So maximizing f, we take its derivative with respect to the PRs, and recall that the S had the form, it was PR times ln PR. So if we take the derivative of this term, we first get an ln PR, and then we get a 1, because the derivative of the logarithm is 1 over PR, which cancels against this one. So we get first a minus kb ln PR minus a kb, and then from this term we get a minus lambda. And so what we can conclude now is that the PR is something, but what is important is that the kb and the lambda, they do not depend on r, which means that for each r we find the same number, and so the PR is a constant which is independent of r. You can explicitly calculate what PR is, and then if you do that, you can check for yourself that S is kb times the ln of omega, where omega is just the number of states, so it's the sum over all the states, where it should be kept in mind that all these states have the same energy, which is the energy of the microcanonical ensemble. So this is a nice exercise to check that this holds. Now then we move on to the canonical ensemble, and now we include all the states R, and that means we do not fix the energy. Every energy is allowed. But what we do fix, so it's not the energy of each state, but we fix the expectation value of the energy, because we want to have to, well, of course, if we wouldn't restrict the energy to some value, then the system would go to infinite energy, because that's where its entropy is largest. So to keep the energy within bounds, we fix its expectation value. So the system can still assume any energy, but the expectation value should always be E. The expectation value here, which is defined as the sum over ER times PR. And so if I then use the Lagrange method again, I first have here the entropy. So this is my S. PR times ln PR. Then this is the normalization, the constraint associated with normalization. So this ensures that the sum over the PRs is 1. And this last term, it has a Lagrange multiplier, which I call KB times beta. I have all the freedom to give it a name, and in this case I take it to be KB times beta. And that is the term which fixes the expectation value of the energy. And if I take now the maximum, take the derivative of f with respect to all the PRs, I get this expression. And the difference with what we had before for the microcanonical ensemble is that in this case the PR is no longer independent on R, but it depends on the value of E in that state R. And so what we see is that ln PR is something, all terms which form together a constant, minus beta times ER. So the KBs are, I just divide by the KBs, so that drops out. And so I have that PR is proportional to e to the power minus beta ER, and that's known as the Boltzmann factor. So we have recovered the Boltzmann factor from this general definition of the entropy and maximize that under the constraint that the probability distribution is normalized and that the total energy is fixed to a particular value. And so you see that this is quite a powerful way of deriving ensembles, and we will meet it in a future movie. Finally, we will evaluate the partition function for a non-interacting gas. And we take the gas as consisting of n-point particles, and they move in a volume which is L by L by L, so that's a cube with size L. The partition function is the sum over all the states, e to the power minus beta ER, and beta is 1 over kBt. And so how do we calculate the sum over all the states? Well, that's a sum over space, phase space. It's an integral over phase space, so we have to integrate over all the momenta and over all the positions of the particles. And in order to correct the sum for quantum mechanical effects, we first have to divide by n factorial, because we have indistinguishable particles, and these particles, if we swap two particles, we have the same state, and so all the permutations are in fact identical, so that accounts for this factor of 1 over n factorial. And we cannot distinguish P's and Q's that are too close. Quantum mechanics, the uncertainty relation tells me that I should divide up the phase space into little cubes of size h3n, because we have a 3n dimensional P and Q. And then we have here the Boltzmann factor, which is in this case so this is the energy of the system, but because we have a non-interacting gas, the potential is not present, and we have only kinetic energy. And so this is the kinetic energy of the gas. Now, first of all, let us look at the integral over all the positions. So there's nothing here which relates to Q, so we just have to integrate over all the Q's, and it's a flat function, it's function 1. Because each Q for each particle moves in a volume L by L by L, so it gives me just a volume, and we have n particles, we just get V in the power n, and I have now put these factors here below the E. And now it still seems that this integral over all the P's with this kinetic energy is very difficult, but it turns out to be very simple. And you can see that if you write it out in all the Cartesian coordinates. So what you do is you take, so this is a sum over each particle, and for each particle we have a sum over its 3 Cartesian components. And so the first integral is e to the power minus p1x squared over 2mkt. Then the second, and that's an integral over dp1x, because that's the only p1x dependence that we have, times an e to the power minus p1y squared over 2 mkt, and so we have a dp1z, and then we have a dp2x, a dp2y, etc. And so if you inspect those integrals, you see that they all give you exactly the same value, because the only difference in these integrals is the name of the integrand. Here it's p1x, here it's p1y, but except for the different name of the integration variable, the integrands are exactly the same. And so we can calculate that those integrals as they are just 3n integrals multiplied by each other, and all these integrals look the same. This is what they look like. They are Gaussian integrals, and the Gaussian integral gives you a value of square root of pi divided by the prefactor of this p squared, and that prefactor is 2mkt, so we see immediately that this is the result of this integral. And so we can write the final result then as v in the power n divided by n factorial lambda in the power 3n, where lambda is the square root of h squared over 2mkt. Now this lambda has a dimension of a length, so it's called the thermal wavelength. It's in fact the de Broglie wavelength, the quantum mechanical de Broglie wavelength for a particle at an energy of order kT. And so if you look at this partition function, so remember this was the partition function that we calculated. This partition function, it's dimensionless, because here lambda is a length, so lambda in the power 3n gives me a volume to the power n, and here is also a volume to the power n. The n factorial is dimensionless, and so z is really a sum over the number of states, as it should. And you see that it's just, you have a volume per particle which is defined by its quantum wavelength, and each particle can be surrounded by a box with a side given by that wavelength, and then the partition function tells you just how many boxes I can put in all those volumes. And then I have this extra permutation correction factor. Now we can of course calculate now the f, which is minus kBt ln z, and that can be worked out straightforwardly. So we first get a minus kBt times 3n log of v over lambda to the power 3. Let me make that a capital lambda to keep the notation consistent. And then I have a minus n kbt times ln n minus 1. So this term derives from the Stirling formula applied to this n factorial, which holds for large particle numbers. And so this is the expression for the free energy. And now what you can do is you can calculate, and this is a nice exercise, you can calculate the pressure. So P is minus df dv at constant n and t, and what you will find from that is that P times V is n kBt. So that's the equation of state for the ideal gas. Another thing you can calculate is the energy. We have seen before that the energy can generally be written as minus d ln z d beta at constant n and v. And because beta is 1 over kt, we can immediately translate that as a derivative of ln z with respect to t, and we get an extra prefactor kbt squared. Now the ln z, we know that z, we have just calculated that, that's v to the power n divided by n factorial lambda to the power 3n. So let's put that in. I neglect here the n factorial because that's independent of t, so that doesn't contribute to the derivative. And v and lambda to the third, they appear with power 3n, which I've put in front of the logarithm. And then we realize that lambda was defined as follows: h over square root 2 pi m kbt. And if I put that all in, then an elementary calculation gives you that E is 3 over 2 nkt. And that is a well-known result. It holds not only in the microcanonical ensemble, but it also holds in the canonical ensemble, and it's known as the equipartition. It's a manifestation of the equipartition theorem. And the equipartition theorem is a direct consequence of the analysis that we have made for the integral over the kinetic degrees of freedom. The point is that all these, that this integral over the kinetic energy factorizes in 3n independent integrals, and each integral gives you an independent contribution to z, which then translates into an independent contribution to the energy. And so that's the background of the equipartition theorem, that the terms in the exponent are additive in the energy. So we have here a sum over energies not only for each particle but even for each Cartesian component. And so the integral factorizes and can be written as a product. And because the energy is related to the logarithm of z, that gives you in the end a sum for the energy over all the Cartesian components of all the particles. And that is what leads eventually to E is 3n2 kBt, the equipartition theorem. So that concludes the discussion of the canonical ensemble. So I guess what you need to recall is the fact that the canonical ensemble has this Boltzmann factor e to the power minus beta er, and a central quantity that we always want to calculate is this partition function e to the power minus beta er. If we have the partition function, we can calculate the Helmholtz free energy as minus kBt ln z. That energy is related to energy and temperature, and the entropy as E minus Ts. And we have that we have values for different derivatives of f. So recall that df, if we take this formula, we see immediately that it's dE minus TdS minus SdT. We know from the first law that dE can be written as TdS minus PdV plus mu dN, and then we have the minus TdS minus SdT. So this is minus SdT minus PdV plus mu dN. And that's a result of these two terms cancelling. And so we see that df dt at constant n and v is minus s, df dv at constant t and n is minus p, and df dn at constant t and v, that's the chemical potential mu. So once we have z, we have f, and from f we can calculate everything we want. So that's a general recipe for solving systems in the canonical ensemble.